Welcome back to the deep dive, where we unpack complex ideas, distill them into their essence, and serve them up fresh just for you. Today, we're diving into something incredibly fundamental, yet often completely overlooked: imperfections in solids. Now, the word imperfection might sound negative, but you're about to discover why these so-called flaws are not just unavoidable, but actually incredibly useful, essential even in the world around us. Think about the hidden genius inside your car's catalytic converter. It's all thanks to these atomic level deviations. Our mission today is to take a deep dive into the core concepts, terms, and examples from this crucial area of material science. We want to present it clearly so you, the college student, can truly grasp it, even without needing visuals. We're going to uncover the hidden stories within these materials, showing you why imperfection can often be a material's greatest strength.
Absolutely. And what's truly fascinating here is how these tiny deviations from perfection fundamentally shape material behavior. It's quite remarkable, really. We often assume materials are perfectly ordered, like perfect crystals. But that's rarely the case at the atomic level. And it's precisely these flaws that dictate everything from how strong a metal is to how efficiently a catalyst can clean our air. Their properties are profoundly sensitive to these imperfections. It makes them a crucial area of study for anyone looking to understand or, well, design materials.
Absolutely. So let's truly dive into these tiny architectural anomalies. We're starting with the core concept. Crystalline materials, despite their neat, repeating atomic structures, are never truly perfect. Every single one contains various defects or imperfections. Think of a crystalline defect as a lattice irregularity, usually on the scale of an individual atom, maybe two. We generally classify these into three main types. There are point defects, which affect just one or two atomic positions.
Right, the smallest scale.
Then linear defects, which are one-dimensional, like a line of misaligned atoms.
Like threads running through the crystal.
And finally, interfacial defects, or boundaries, which are two-dimensional surfaces.
Exactly. Boundaries between different regions.
Okay, so to give you a compelling real-world example of why these matter, let's go back to that catalytic converter. This device, usually found in your car's exhaust system, works its magic because pollutant gases actually attach to specific surface defects on the crystalline metallic materials inside. While attached to these precise spots, the molecules undergo chemical reactions that convert them into, well, less polluting substances.
It's chemical transformation happening right on those flawed surfaces.
Exactly. Imagine toxic carbon monoxide, for instance, being transformed into carbon dioxide,
Yeah.
or harmful nitrogen oxides becoming harmless nitrogen gas. Visually, if you could picture it, you've got your car's exhaust pipe, and inside a stainless steel casing, there's this ceramic block. It looks a bit like a honeycomb, and it's coated with a metallic catalyst.
Usually platinum, palladium, rhodium, those kinds of metals.
Right. So the exhaust gases, loaded with hydrocarbons, carbon monoxide, and nitrogen oxides, flow over this catalyst. They stick to its surface defects, they react, and then they exit as mostly water, carbon dioxide, and nitrogen. It's truly a marvel of materials engineering, literally cleaning up our act, one defect at a time.
It really is. And to elaborate on the simplest of these, the point defects, let's start with vacancies. A vacancy is simply a vacant lattice site, an atom missing from its normal position in the crystal structure, just an empty spot where an atom should be. And these aren't just accidental, mistakes in the structure. Thermodynamics actually dictates their presence.
Thermodynamics, how so?
Well, they exist because introducing a small number of vacancies increases the overall entropy, or randomness, of the crystal. And nature tends to favor states with higher entropy, at least at temperatures above absolute zero. The key takeaway here is that the equilibrium number of these vacancies, we call it NV, depends exponentially on temperature.
Exponentially, meaning?
Meaning as you increase the heat, the number of empty sites increases dramatically, not just linearly, but much faster. There's an equation for this, equation 4.1 in the text, NV and XPQ VKT. Here, N is the total number of atomic sites. QV is the energy needed to form a vacancy. It takes energy to pop an atom out of place.
Okay.
T is the absolute temperature in Kelvin, and K is Boltzmann's constant. The exponential term, XPQVKET, really drives the number up as P increases. Just to give you a feel for it, for most metals, just below their melting temperature, about 1 in every 10,000 lattice sites is empty.
1 in 10,000. That sounds small, but considering how many atoms are in even a tiny piece of metal.
Exactly. It adds up to an astonishing number of empty spots. The text walks through an example calculating the number of atomic sites in copper. You use its atomic weight, density, Avogadro's number. You end up with something like 8 times 10 to the 28 atoms per cubic meter. It's huge.
Mind-bogglingly huge.
And then, using that equation, Even at 1,000 degrees Celsius, which is hot but still below copper's melting point, you calculate the number of vacancies. With an activation energy QV of about zero point 0.9 electron volts per atom, you get around 2.2 times 10 to the 25 vacancies per cubic meter.
So billions upon billions, trillions of trillions, really, of these tiny empty spots that really drives home how fundamental these imperfections are.
It does. They're not just rare anomalies. They're an inherent part of the crystal structure at any temperature above 0 Kelvin.
Okay, so vacancies are missing atoms. What else falls under point defects?
The other main type is a self-interstitial. Picture a host atom, one that belongs in the crystal, getting squeezed into a tiny void space between other atoms, a spot that's normally unoccupied.
So not replacing an atom, but wedged into a gap.
Precisely. If you imagine that perfect grid of atoms again, like figure 4.1 shows conceptually, a vacancy is an empty spot in the grid. A self-interstitial is like an extra atom forced in between the regular grid points.
That sounds like it would cause more disruption.
It does. Because that extra atom is usually much bigger than the interstitial space itself, these defects create significant distortions in the surrounding lattice. They push the nearby atoms out of place quite a bit. This makes them energetically less favorable to form, meaning they're much less probable and exist in significantly smaller concentrations than vacancies. You just don't find as many of them.
Got it. So vacancies are common, self-interstitials are rarer because they distort things more.
Exactly. Now, from missing or extra host atoms, we can shift our focus to foreign atoms. What happens when impurities sneak into a crystal?
Ah, right, because perfectly pure materials are almost impossible to get in reality.
Correct. That opens up a whole new world of imperfections and opportunities with impurities in solid solutions.
And here's where it gets really interesting, I think. You might think of pure metals as having only one type of atom, but truly pure metals are incredibly rare. Even something labeled, say, 99.99999% pure still means billions of impurity atoms per cubic meter.
Absolutely.
Hmm.
Often, though, impurity atoms aren't accidental. They're intentionally added to metals to create alloys.
Like adding zinc to copper to make brass, or copper to silver for sterling silver.
Exactly. These additions are made to enhance specific properties, maybe make the material stronger, more corrosion resistant, or easier to shape. It's a huge part of materials engineering.
So how do these impurity atoms fit in?
When these impurity atoms are added, they don't just sit on the surface or form separate clumps. Assuming they dissolve properly, they incorporate themselves into the solid structure, forming what we call a solid solution. Think of it like mixing water and alcohol. The original crystal structure is maintained, no new structures form, and the impurity atoms are randomly and uniformly dispersed within the host lattice.
Okay, like a uniform mixture, but in a solid state.
Precisely. We call the host material, the one present in the greatest amount, the solvent, and the impurity, in minor concentration, the solute, just like in liquid solutions.
Makes sense. And how do these solutes fit in? Are there different ways?
Yes, there are two main types of impurity point defects in solid solutions. First, you have substitutional solid solutions. Here, the solute atoms, the impurity atoms, literally replace host atoms in the lattice. They sit on the regular lattice sites.
So they swap places with the original atoms.
Essentially, yes.
Yeah.
Figure 4.2 in the text shows this nicely. Imagine that 2D grid again, and one of the grid points is now occupied by a different type of atom, maybe slightly larger or smaller. That's substitutional. Now, the degree to which a solute will dissolve substitutionally depends on several factors, often summarized by the Hume-Rothery rules.
Hume-Rothery rules. Okay, what do they tell us?
They basically give us guidelines for predicting solubility. There are four main rules. One, the atomic size factor. The difference in atomic radii between the solute and solvent atoms must be less than about plus or minus 15%. If they're too different in size, they won't substitute easily.
So size matters.
Very much. Two, crystal structure. Both the solute and solvent metals must have the same crystal structure. FCC dissolves better in FCC, BCC in BCC, and so on.
Like fitting puzzle pieces of the same shape?
Good analogy. Three, electronegativity. The two atom types should have similar electronegativities. If there's a large difference, they tend to form distinct intermetallic compounds instead of a solid solution.
Meaning they'd rather bond chemically than just mix.
Exactly. And four, valences. All else being equal, a metal tends to dissolve another metal of higher valency more readily than one of lower valency. A classic example where all these rules are met really well is copper and nickel. Their atomic radii are close, 0.128 millimeter versus 0.125 millimeters. Both are FCC, electronegativities are similar, valencies are compatible. As a result, they are completely soluble in each other in any proportion.
A perfect match, like you said. Okay, that's substitutional. What's the other type?
The second type is an interstitial solid solution. In this case, the impurity atoms don't replace host atoms. Instead, they fill the small voids or interstices between the host atoms. Look back at that figure 4.2 concept. You'd see a much smaller impurity atom squeezed into a gap between the larger host atom.
Like the self-interstitial, but with a foreign atom this time.
Precisely. These interstitial sites exist in specific locations within crystal structures. In FCC and BCC, common ones are called tetrahedral sites, surrounded by 4 host atoms, and octahedral sites, surrounded by 6. Figure 4.3 shows where these sites are located within the unit cells. For FCC, for example, there's an octahedral site right in the center of the unit cell and also at the center of each edge.
So specific geometric locations where small atoms might fit.
Exactly. The key constraint here is size. Interstitial impurities must be substantially smaller than the host atoms to fit into these voids. Even then, they typically introduce some lattice strains because the voids are quite small. There's an example problem 4.2 that calculates the radius r of an atom that just fits into a BCC octahedral site. It turns out to be only about 15.5% of the host atom radius r. So r equals drain sway 155r. Very small.
So not much room in there.
Not much at all. This size limitation and the resulting lattice strain means the maximum concentration of interstitial impurities is typically low, usually less than 10%, often much lower. A classic example is carbon and iron, which forms steel. Carbon's radius, 0.071 millimeter, is much smaller than iron's, 0.124 millimeter, so it fits interstitially. But the maximum solubility is only about 2%.
Okay, that makes sense. So thinking about those two types, expert, if someone asked why can you get complete solid solubility for substitutional solutions like copper nickel, but never for interstitial solutions, how would you break that down for them?
Oh, that's a great question that gets right to the heart of it. The simplest answer lies in those size constraints we just talked about. Interstitial sites are always much smaller than the host atoms. So any impurity atom you squeeze in there, no matter how small, is going to cause some distortion, some lattice strain. This inherent strain limits how much you can dissolve before the structure becomes unstable or changes. With substitutional solutions, however, if the atoms satisfy those Hume-Rothery rules, especially similar size, crystal structure, and electronegativity, they can swap in and out almost perfectly, like identical twins taking each other's places. There's minimal disruption to the overall lattice, allowing for potentially complete solubility across the entire composition range. It's fundamentally about how well the impurity fits into the existing atomic neighborhood without causing too much trouble.
That's a really clear distinction. Thanks. Now let's move on from these point-like imperfections, these zero-dimensional defects, to one-dimensional defects. Linear defects, also known widely as dislocations. These are, as the name suggests, linear defects where atoms are misaligned. Think of them as tiny imperfections running along a line within the crystal structure.
Right. Not just a single point, but extended along a line.
The first type is an edge dislocation. The textbook description uses the idea of an extra half plane of atoms terminating within the crystal. Imagine, like in figure 4.4, a stack of neatly aligned atomic planes, perfectly regular. Then picture an extra half plane inserted from the top, but it only goes partway down. Its edge ends abruptly inside the crystal.
Like inserting a bookmark only halfway into a book.
Exactly. The dislocation line runs along this terminating edge, perpendicular to the page in that diagram. This insertion causes distortion. The atoms above the line near the extra half plane's edge are squeezed together, compressed. And the atoms below that edge are pulled apart, in tension. It's often represented by an inverted T symbol, indicating that edge.
That distortion is key. Then there's the screw dislocation. This one's a bit harder to visualize, perhaps. Imagine you make a cut partway through a perfect crystal block. Then you apply a shear stress, pushing the crystal on one side of the cut forward relative to the other side by exactly 1 atomic spacing. This shift creates a kind of spiral ramp around the line where the shearing happened. Figure 4.5a tries to show this shear producing the defect. Figure 4.5b shows what happens if you try to trace the atomic planes around the dislocation line. You follow a spiral path, like walking up a spiral staircase or turning a screw.
Ah, hence the name screw dislocation.
Precisely. The dislocation line in this case is parallel to the shear direction and the axis of the helix. It's often represented by a little spiral symbol. In real materials, though, dislocations rarely exist as pure edge or pure screw types along their entire length. Most are combinations of both, called mixed dislocations.
So they can curve and change character.
Yes. Imagine a dislocation line, like the one in figure 4.6 that curves through the crystal. At one point, it might be pure screw in character. At another point, it might be pure edge. And in between, It has components of both. It's mixed.
Okay, so edge, screw, and mixed. Now, to really understand these, there's a critical concept, the Berger's vector, usually denoted by B.
Yes, the Berger's vector is fundamental. It's a vector that defines both the magnitude and the direction of the lattice distortion associated with the dislocation. Think of it as measuring the amount of slip or displacement caused by the defect.
And how does it relate to the different types?
There are crucial relationships. For an edge dislocation, the Berger's vector is always perpendicular to the dislocation line, that terminating edge of the half-plane. For a screw dislocation, the Berger's vector is always parallel to the dislocation line, the axis of the spiral ramp. And for a mixed dislocation, as you might expect, the Berger's vector is neither perpendicular nor parallel to the dislocation line at that point.
So the orientation of B relative to the line tells you the character.
Exactly. And what's really important is that the Berger's vector itself, its magnitude and direction, remains constant along any single continuous dislocation line, even if the line curves and its character changes from edge to mixed to screw.
Okay, that's a key point. And why are these dislocations, these linear defects, so incredibly important?
Their primary importance lies in plastic deformation. That's the permanent shape change metals undergo when you bend them, stretch them, or hammer them. Dislocations are the microscopic mechanism that allows this to happen.
So how do these tiny lines allow a whole piece of metal to bend?
It's fascinating. Imagine trying to slide a heavy rug across a floor. It's hard to slide the whole thing at once. But if you create a wrinkle or a ruck in the rug, you could push that wrinkle across much more easily. Dislocations act like that wrinkle at the atomic level. When you apply stress to a crystalline material, it's much easier for these dislocation lines to move through the lattice than it would be to slide entire perfect planes of atoms past each other simultaneously. The movement of a dislocation effectively shifts one plane of atoms relative to the next, one atomic step at a time. The cumulative effect of many dislocations moving is the macroscopic plastic deformation you observe.
Ah, so they facilitate slip between atomic planes.
Precisely. Without dislocations, crystalline materials, especially metals, would be incredibly strong but also very brittle. They'd shatter like glass instead of bending. Understanding how dislocations move, interact, and multiply is absolutely fundamental to understanding mechanical properties like strength and ductility. And we can actually see them. Using techniques like transmission electron microscopy, TEM, we can directly image these defects. Figure 4.7 shows a TEM image of a titanium alloy, and you can clearly see these dark, thread-like lines tangled within the grains. Those are the dislocations.
Amazing that we can visualize these atomic scale lines. Okay, from points 0D and lines 1D, let's broaden our scope again to interfacial defects, or two-dimensional imperfections. These are boundaries, surfaces, essentially, that separate regions within the material that have different crystal structures or different crystallographic orientations. The most obvious one, I suppose, is the external surface itself, the surface of any solid object.
Right. Atoms at the surface aren't fully bonded like the atoms in the interior. They have unsatisfied bonds, dangling bonds, which gives them a higher energy state. This excess energy is called surface energy, or surface tension. Materials naturally try to minimize their total surface energy, which is why liquids form spherical droplets, for example, to minimize surface area.
Okay. What about internal boundaries?
Inside a material, especially if it's polycrystalline, made up of many small crystals or grains, you have grain boundaries. Imagine building a wall with perfectly aligned bricks, but then next to it you start another section where the bricks are tilted or rotated slightly differently. The interface where these two differently oriented sections meet, that's a grain boundary. So it's the boundary separating two small grains or crystals that just have different crystallographic orientations. Figure 4.8 gives a schematic of this. You see atoms lined up one way on one side, a different way on the other, and a region of mismatch in between.
And this mismatch region must have some extra energy, too.
Yes, absolutely. The atoms along the boundary are also not perfectly bonded, leading to a grain boundary energy, similar to surface energy. We distinguish between small-angle grain boundaries, where the misorientation between grains is just a few degrees, and high-angle grain boundaries with larger misorientations. Interestingly, a small-angle boundary, specifically a tilt boundary, can actually be described as an array of edge dislocations lined up. Factor 4.9 shows this a series of parallel edge dislocations, creating that slight tilt between the two grains.
So dislocations can arrange themselves to form a boundary?
They can. The grain boundary energy generally increases as the angle of misorientation increases, up to a certain point. These boundaries are also regions of higher chemical reactivity, and impurity atoms often tend to segregate or gather there. Also, at high temperatures, grains tend to grow larger grains, consuming smaller ones, as a way for the material to reduce the total amount of high-energy grain boundary area. This affects properties, especially at high temperatures.
Interesting. Are there other types of internal boundaries?
Yes, briefly we should mention phase boundaries. These exist in materials that contain multiple phases, that is, regions with distinct physical or chemical characteristics, like different compositions or crystal structures. The interface between these different phases is a phase boundary. And then there are twin boundaries. These are a special type of grain boundary across which there's a specific mirror lattice symmetry. Imagine, as shown conceptually in figure 4.a, a clear boundary line. The arrangement of atoms on one side is a mirror image of the arrangement on the other side. The region between the original crystal and its mirrored twin is the twin. These can form either through mechanical shear forces during deformation, we call those mechanical twins, or sometimes during annealing heat treatments, annealing twins. You can often see them as distinct bands within grains and micrographs.
Okay, surfaces, grain boundaries, phase boundaries, twin boundaries, lots of different interfaces.
Indeed. And now, let's circle back one more time to our catalytic converter example, because these interfacial defects, particularly surface defects, are absolutely critical for its function. This ties into the materials of importance section on catalysts. Remember, a catalyst speeds up a reaction without being consumed. Solid catalysts work because reactant molecules from the exhaust gas, in this case adsorb, meaning they stick, onto the catalyst surface. But not just anywhere on the surface.
They stick to the defects.
Primarily, yes. Think of an idealized, perfectly smooth atomic surface. Now imagine the real surface, as depicted schematically in figure 4.11. It has imperfections. There are steps or ledges where one atomic plane ends, sharp corners or kinks at these ledges, flat areas called terraces, occasional missing atoms, surface vacancies, and even individual atoms sitting on top of terraces, adatoms. These defect sites, the ledges, kinks, vacancies, atoms, are often much more reactive than the atoms on a perfect terrace. They have different bonding environments, making them prime locations for molecules to adsorb and then react.
So the flaws on the surface are actually the active sites.
Exactly. In the catalytic converter, pollutants like CO, NOx, and hydrocarbons pass over catalysts like cerium zirconium oxide, often with precious metals dispersed on them. The molecules adsorb onto these surface defect sites. NOx might dissociate into N and O atoms at one type of site. O2 might dissociate into O atoms at another. Then these atoms can recombine. N atoms form N2 gas, CO reacts with O atoms to form CO2, hydrocarbons react with O atoms to form CO2 and H2O. High-resolution microscopy, like the TEM image in figure 4.12 of a CO.5 0.5 O2 catalyst particle, actually allows us to see these surface ledges, kinks, and facets that act as the crucial adsorption and reaction sites. It's defects doing the work.
That really ties it all together beautifully. So surface defects are critical for catalysis.
Absolutely. And just for completeness, we should mention there are also larger scale defects, sometimes called bulk or volume defects, things like pores, empty spaces, cracks, or foreign inclusions, little bits of unwanted material trapped inside. And even atomic vibrations, the fact that atoms are constantly jiggling around their average lattice positions, can be considered a type of imperfection, especially since the amplitude increases with temperature, influencing many properties.
Right, so imperfections exist at all scales, from single atoms missing to large cracks, and even just the inherent vibration. Now that we've explored what these imperfections are, let's turn our attention to seeing the invisible microscopic examination. It's one thing to talk about vacancies and dislocations, but how do we actually see them, or at least see their effects? This involves examining the material's microstructure.
Right, the microstructure encompasses all these structural features we've discussed. Grains, grain boundaries, phases, defects that influence the material's properties. Many of these features are microscopic, meaning they're on the scale of microns, millionths of a meter, or smaller, so we need special tools. Although, some features can be macroscopic. For example, figure 4.13 shows a cross-section of a copper ingot where you can actually see large, needle-shaped grains radiating outwards with the naked eye. But usually we need magnification.
And why is looking at the microstructure so important?
Oh, it's vital for so many reasons. It helps us understand why a material behaves the way it does, predict its performance under different conditions, helps in designing new alloys with specific properties, ensures that manufacturing processes like heat treatment were done correctly, and it's crucial for analyzing failures, finding out why a part broke by looking at its fracture surface and internal structure.
Okay, so how do we do it? What are the tools?
The most traditional tool is optical microscopy, sometimes called light microscopy. For opaque materials like metals and many ceramics, we usually use it in a reflecting mode. Light shines down onto the sample surface and reflects back up into the microscope. But you can't just look at a lump of metal. You need careful preparation, called metallography. First, you grind the surface flat, then polish it progressively using finer and finer abrasives until it's like a mirror, free of scratches. Then comes the crucial step, etching. You briefly apply a chemical reagent that selectively attacks the polished surface.
Etching, how does that reveal the structure?
It works in a couple of ways. First, chemical reactivity often varies slightly depending on the crystallographic orientation of each grain. So the etchant might dissolve atoms from differently oriented grains at slightly different rates, creating different surface textures or levels of reflectivity. Some grains appear bright, others darker. Second, grain boundaries are typically regions of higher energy and often etch more rapidly than the bulk grains. This creates tiny V-shaped grooves along the boundaries. So under the microscope, as shown conceptually in Figure 4.14, you see distinct grains, often with different shades or textures. And Figure 4.15 shows how those etched grooves at the grain boundaries scatter light away, making the boundaries appear as dark lines outlining the grains. You might also see features like twin boundaries within the grains.
So etching brings out the map of the grains and boundaries. What's the limit for optical microscopes?
The useful upper magnification limit for optical microscopy is typically around 2000x. Beyond that, you start running into the fundamental limits set by the wavelength of visible light. You can't resolve finer details.
Okay, so for higher magnifications, what do we use?
For higher magnifications, we need electron microscopy. These techniques use beams of electrons instead of light. Because electrons can have much shorter wavelengths than visible light, they allow for significantly higher resolutions and magnifications.
Makes sense. Are there different types of electron microscopes?
Yes, two main types are commonly used in material science. The transmission electron microscope, or TEM. In TEM, a high-energy electron beam actually passes through a very thin foil specimen. The sample has to be incredibly thin, maybe only tens or hundreds of nanometers thick. The way the electrons interact with the material as they pass through creates contrast, revealing internal microstructural features and defects like dislocations, precipitates, and grain boundaries at very high resolution. TEM can achieve magnifications up to and even exceeding 1 million x. It's how we get those images of individual dislocations we mentioned earlier.
Wow, through the sample. What's the other type?
The other is the scanning electron microscope, or SEM. In SEM, a focused electron beam is scanned across the surface of the specimen. Instead of passing through, the image is formed primarily from electrons that are reflected or scattered back from the surface, backscattered electrons, or from secondary electrons knocked out of the surface atoms by the beam. SEM provides excellent images of surface features, think fracture surfaces, surface topography, particle shapes. It has a fantastic depth of field, which gives the images an almost three-dimensional appearance. Magnifications typically range from maybe 10x up to over 50,000x, sometimes even higher. One thing to note is that if your sample isn't electrically conductive, you usually need to apply a very thin metallic coating, like gold or carbon, to prevent charge buildup from the electron beam.
So TEM for internal details at ultra-high magnification, SEM for surface features with great depth. Got it. Is there anything even more powerful?
Yes, there's been a revolution in recent decades with scanning probe microscopy, or SPM. These techniques are fundamentally different. They don't use light or electron beams in the traditional sense. Instead, SPM generates a topographical map of the surface, often with atomic-level resolution. It uses a tiny, incredibly sharp probe or tip that is scanned across the specimen surface, kept extremely close, sometimes just fractions of a nanometer away. Various interactions between the probe tip and the surface, like quantum mechanical tunneling currents or atomic forces, are measured with extreme precision. These measurements are then used by a computer to construct a detailed, often three-dimensional image of the surface topography. SPM offers incredibly high magnifications, potentially up to 109x, allowing visualization of individual atoms on some surfaces. It provides unparalleled resolution and can operate in various environments, vacuum, air, even liquid. Its development was a key enabler for the whole field of nanotechnology and nanomaterials.
1 billion times magnification. That's almost hard to comprehend. Seeing individual atoms.
It really is remarkable. Figure 4.16 shows some bar charts comparing the size ranges of different features, from atoms up to macroscopic structures, and the resolution capabilities of different techniques: naked eye, optical, SEM, TEM, and SPM. It clearly highlights how SPM pushes the boundaries of what we can see down at the atomic scale.
Fantastic overview of the tools. Now let's connect this back to a practical application. Quantifying imperfection grain size determination. You mentioned grain boundaries earlier, and we can see grains with microscopy. Why is measuring the size of these grains important?
Grain size is critically important because it significantly influences many mechanical properties of polycrystalline materials. For example, materials with smaller grains, finer grain materials, are generally stronger and harder at room temperature than the same material with larger grains. So controlling grain size during processing is a key way to tailor material properties.
Okay, so we need ways to measure it reliably. How is it done?
Traditionally, and still used as a basis even with automated digital image analysis today, there are a couple of standard quantitative methods. One is the linear intercept method. Here's how it works. You take a photomicrograph at a known magnification. You then draw several random straight lines across the micrograph. You count the total number p of times these lines intersect grain boundaries. You also measure the total length LT of all the lines you drew. Then the mean intercept length, which we call lowercase a, and which represents the average grain dimension, is calculated using equation 4.16. A as LTPM, where M is the magnification of the micrograph.
So lengths divided by intersections adjusted for magnification?
Exactly. There's an example, 4.5, that walks through this. First, you might need to determine the magnification M if it's not given directly. Often, micrographs have a scale bar. You measure the length of the scale bar on the image and divide it by the actual length it represents, like 100 micrometers. That gives you M using equation 4.20. Then you plug LT, P, and M into the formula to get M.
Okay, seems straightforward enough. What's the other method?
The other widely used technique is the comparison method, which is standardized by organizations like ASTM, American Society for Testing of Materials. This method uses standard comparison charts. These charts show images of idealized grain structures at different average sizes, usually all presented at a standard magnification of 100x. Each standard image is assigned an ASTM grain size number, denoted by G. The numbers typically range from 1, very coarse grains, up to 10 or higher, very fine grains. To use it, you take a micrograph of your specimen, also at 100x magnification if possible, and you visually compare it to the standard charts to find the one that matches best. That chart's G value is then assigned as the grain size number for your sample.
So a visual comparison to standards. What if your micrograph isn't at 100x?
There are formulas to handle that. The fundamental relationship is equation 4.17, n equals 2 G-1. Where n is the average number of grains per square inch when viewed at 100x magnification. If your micrograph is taken at a different magnification, m, you use equation 4.18, which adjusts for the magnification difference. Nm, M102 equals 2G1, where Nm is the number of grains per square inch measured on your micrograph at magnification m. The key thing to remember is that a higher grain size number G means a smaller average grain size. It's an inverse relationship in that sense.
Yeah.
There are also formulas, equations 4.19a and 4.1b, that directly relate the grain size number G to the mean intercept length we calculated earlier, so you can convert between the two measures. The example problem 4.5 finishes by calculating G from the previously determined value.
Okay, so two main ways to put a number on grain size. Measuring intercepts or comparing to standard charts. Both crucial for controlling material properties.
Precisely. These quantitative measures are essential for quality control, material specifications, and research.
And there you have it. Wow, we've really journeyed through the world of imperfections and solids today. We've covered everything from single missing atoms, vacancies, to extra atoms squeezed in, interstitials.
To impurities forming solid solutions, governed by those Hume-Rothery rules.
Then the linear defects, dislocations, edge, screw, and mixed, and that all-important Burger's vector.
And finally, the interfacial defects. Surfaces, grain boundaries, phase boundaries, twin boundaries.
And how all these subtle imperfections are not just flaws, but often deliberate, engineered features, or at least inherent characteristics, that give materials their unique strength, their catalytic abilities, their very workability.
It really underscores the idea that perfection isn't always desirable or even possible in material science. The flaws are often where the interesting properties come from.
It really shows how even the smallest details, things happening at the atomic scale, can have monumental impacts on the macroscopic world we interact with every day.
And this naturally leads to a thought-provoking question for you, the listener, to consider. Knowing now how critical these imperfections are, how might you intentionally introduce or manipulate specific types of defects? Perhaps through clever alloying or carefully controlled heat treatments, or maybe even novel processing techniques like 3D printing or severe plastic deformation. How could you use these imperfections to design and create materials with entirely new or significantly enhanced properties for the future?
A fantastic challenge to ponder.
The deep dive has hopefully given you a new lens, a new appreciation for viewing the intricate and often imperfect, yet incredibly functional world of material science.
Thank you so much for joining us on this deep dive into imperfections and solids. We hope you feel a little more well-informed, maybe a lot more curious about the invisible world hiding within the materials all around us. Until next time, keep exploring. This has been a special deep dive from the Last Minute Lecture team.